immediately after Schrödinger and before that Heisenberg wrote down the papers on quantum mechanics, after about a year or so, Dirac presented his own formalism of quantum mechanics, and very soon he published one of the classic texts on quantum mechanics. He introduced the Bra and Ket algebra and also provided a very elegant and extremely elegant formulation of quantum mechanics. We will continue our discussions on this formalism. However, before that, I thought I will mention that Albert Einstein, who is regarded as one of the most outstanding physicists of all times, had said about Dirac's work that Dirac, to whom in my opinion we owe the most logically perfect presentation of quantum mechanics. This I have quoted from a book by Professor Mukunda, in which he made this quotation. So, Dirac's formalism of quantum mechanics is, as according to Einstein, is the most logically perfect presentation of quantum mechanics. The references will be of course, the classic text on this subject is Professor Dirac's book, which is entitled Principles of Quantum Mechanics and published by Oxford University Press, and I think in 1958 it was the 4th edition of his famous book. The book came out just after, in the late 20s actually. We have, as I have been mentioning, our own book on quantum mechanics, and in which we have given the formulation that I will be following in this and the following lectures. There is also a very nice book by J. Townsend on, actually the title of the book is The Modern Approach, A Modern Approach to Quantum Mechanics. It is published by McGraw-Hill in 1992. Of course, there are many numerous books. There is a book by Gordon Boehm and of course, the famous Feynman Lectures on Physics, volume 3, and I will advise all of you to go through that, the Feynman Lectures, volume 3. So, we consider a dynamical system, and a dynamical system can be a linear harmonic oscillator or just an electron or a hydrogen atom or a diatomic molecule or something like that. Now, each state of the dynamical system can be represented by a certain type of vector, and in order to, by a certain type of Ket vector, which we write like this, and in order to distinguish it from other vectors, we put a symbol, so that a state of a dynamical system can be represented by a Ket vector, which is known as the Ket vector, and which forms a dual vector space. And the vector space is linear in the sense that if we have another vector b, then another Ket vector b, then the linear combination C1a plus C2b, where C1 and C2 are complex numbers, is also a vector in the same space. Now, I will quote from Professor Dirac's book on quantum mechanics, and let us read this through. I mean, if you want to read the original quotation, it is of course given in his book, but let us read this through slowly. Each state of a dynamical system at a particular time corresponds to a ket vector. The correspondence being such that if a state results from the superposition of certain other states, its corresponding ket vector is expressible linearly in terms of the corresponding ket vectors of the other states and conversely. So, this is introduced in a slightly abstract manner, but we hope we will get a physical understanding of this shortly. Then it is a dual vector space, so that corresponding to the ket A there is a unique bra A, and there corresponding to a ket B there is a bra B, such that bra A ket B is a complex number, C number. C number means it is a complex number, and this quantity is known as the scalar product of the vector A with vector B, and as such this is an axiom. Axiom means something like an assumption. There is no proof of this. So, according to this axiom, the complex conjugate of this number is equal to B A. If A B1 is equal to A B2 for any ket vector A, for any bra A, then we say that B1 is equal to B2. Similarly, if A1 B is equal to A2 B for any ket, for an arbitrary ket B, then we say that bra A1 is equal to bra A2. So, the equality is through the scalar product. Similarly, if bra A ket B is 0, is a null ket for any bra A, then ket B is said to be a null ket. Similarly, if bra A ket B is in 0 for any ket B, then bra A is a null bra. And similarly, if I have A, if this is 1, then the ket A is said to be normalized, Now, we had said that A, B, the complex conjugate of that is equal to B A. So, if B is A, that is, if ket B is equal to A, then bra B is equal to bra A, then I can write down that A bar is equal to A. So, that this quantity is real. We further assert, this is also we further assert that bra A ket A is always a positive definite equal to 0 if and only if ket A is a null ket. So, if the scalar product of a ket with its own bra is always positive, if it is 0, then ket A must be a null ket, and bra A, corresponding bra A will be also a null bra. Now, if I have, this is the linearity relation, if I have P is equal to C 1 A plus C 2 B, then bra P is equal to C 1 star, this is a complex number, C 1 star bra A plus C 2 star bra B. This is the linearity relation. And if, as I had mentioned yesterday, if ket A corresponds to a state whose wave function is given by, say, psi of r in the Schrodinger representation, and if bra B, ket B is represented by the state which is represented by the wave function phi, the corresponding ket vector is B, the state of the system or of the harmonic oscillator or of the hydrogen atom is given by psi of r, and if its ket vector is denoted by A, then the relationship is through the scalar product, that is B A will be equal to phi star psi d tau integrated over the entire space. So, this is the scalar product. And finally, if A B is 0, if this is a 0 number, then these two kets are said to be orthogonal to each other, orthogonal to each other. Now, let me just to make things simple, let me consider a 2-dimensional space. We can consider a 3-dimensional space also, or a 4-dimensional space, but just for the sake of simplicity, we have, let us suppose ket A is represented by, say, 1 I, then bra A, let me put a 1 over under root 2 sign, will be equal to 1 over root 2, this will be the corresponding. In order to understand the Bra Ket algebra, one can consider examples from theory of matrices, and then everything becomes clear. So, you will have bra A ket A will be equal to 1 over root 2 1 minus I 1 I. So, this is 1 times 1 is 1, 1 over root 2 times 1 over root 2. So, this is 1 over root 2 whole square. So, that is 1 over 2. So, this becomes 1 over 2 into 2. So, this is 1. So, it is a normalized ket. So, it is a normalized state. Similarly, if I consider a bra B ket B as, let us suppose, 1 over root 2 1 minus 1, then bra A ket B will be equal to, bra A is 1 over root 2 times 1 over root 2 is half, and then 1 minus I, 1 minus I. So, this is 1 minus minus is plus, I square is minus 1. So, 1 minus 1 is 0. So, we say that these two kets, this A and B, are orthogonal. We say that A and B are orthogonal vectors, are orthogonal vectors. We can consider another example in 3-dimensional space. Let us suppose in a 3-dimensional space we write A is equal to 1 0 0 and B is equal to, just to make life simple, 0 1 0. Both of them have unit length, because Bra A Ket A will be 1 0 0 1 0 0 and this will be just 1. And similarly, Ket B is also a normalized ket, but Bra A Ket B will be equal to 0. So, this is how we understand. Let us consider, go back to a 2-dimensional space, and let us suppose A is equal to A B, where A and B are complex numbers. So, then Bra A will be equal to A star B star. It is a dual vector space. So, corresponding to every column vector there is a row vector. So, Bra A Ket A will be A star, that is mod A square plus mod B square, and if this is 0, then A must be 0 and B must be 0. So, if this the scalar product is 0, so then A must be equal to 0 0. This is a null ket, because you consider any Bra B, say C D, if I write down Bra B Ket A, so this will be, sorry, this is Bra B, I am sorry, this is Bra B. So, this will be C D 0 0, so this is 0. So, this is a null ket, a null vector in a 2-dimensional space. You can consider a 3-dimensional space or a 4-dimensional space, and so on. Now, as we know that in the theory of matrices, one vector, let us suppose I consider a 2-dimensional vector 1 1, if I multiply this by a vector like this, a square matrix like this, it transforms to another vector. Let us suppose let me put it like this, 1 1 1 1. So, this becomes, this is not a good example, because let me redo the example. So, we have here, for example, say 1 1 2 2, and this is, let us suppose, 1 and 4. So, this operating on that, so this will be 1 times 1 is 1, 9, 2 plus 4, 6. So, a square matrix operating on a vector transforms to another vector. So, we say that we consider a linear operator alpha, which if operates on A, it transforms to another vector B, and this transformation is linear. Linear meaning that alpha something like A plus C, let us suppose, this is equal to alpha operating on A plus alpha operating on C. So, it is a linear operator. I can have in fact alpha, a linear operator, alpha operating on C1 A1 plus C2 A2 plus C3 A3, where C1, C2, C3 are all constants, are all complex numbers. Then this is equal to C1 alpha A1 plus C2 alpha A2 plus C3 alpha A3, etc. So, this is a consequence of the linearity. Then we say that two operators alpha and beta are said to be equal if and only if I write two f's here, that means if and only if alpha A, this scalar product, is equal to B alpha A, A alpha A for any ket A. I am sorry, this is A beta A. If I consider two linear operators alpha and beta, and if this equality holds for any ket vector A, then we say that alpha and beta are equal. If alpha operating on ket A is a multiple of ket A, if alpha operating on ket A is a multiple of ket A, then we say that ket A is an eigenket of the operator alpha belonging to the eigenvalue C, which in general can be complex. So, this equation, when an operator operating on a ket gives you a multiple of the same ket, then this equation is known as an eigenvalue equation. This equation is known as an eigenvalue equation. I will give you an example. Let me consider this 0, 1, 1, 0. Now, if I multiply this, if I operate this on 1 and 2, let us suppose, then you can see 0 times 1 is 0, 1 times 2 is 2, and 1 times 1 is. So, please see, this is not a multiple of this. So, this is not an eigenvalue equation. On the other hand, if I write like this 0, 1, 1, 0 operating on 1, say minus 1. So, you will get 0 times 1 is 1, 1 times minus 1 is minus 1, 1 times 1 is 1. This ket is a multiple of this ket. In fact, the multiplication constant is minus 1. So, this is an eigenvalue equation. 1 minus 1 is an eigenvector of this square matrix, and the eigenvalue is minus 1. Let me take another example, 0 1 1 0. If I operate this on 1 1, then I will get 1 1. So, the eigenvalue is plus 1. So, this is not an eigenvalue equation. So, 1 2 is not an eigenvector of this equation, but 1 1 and 1 minus 1, as you must have read from your theory of matrices, are both eigenvectors of the operator this. So, finally, if the operator alpha operating on a ket vector produces a multiple of a ket vector, then we say that this represents an eigenvalue equation. Now, we next define the adjoint of the operator alpha, and we denote this adjoint following Dirac's notation by alpha bar. This is defined like this. So, it is the definition is through this equation, that A alpha bar B. You see, if I know this scalar product for any bra A and any ket B, then I know alpha bar, and this by definition is equal to, in the reverse order, B alpha A, which is a complex number, this. So, you have, so let me calculate what is the adjoint of alpha bar. So, let me put this as beta. So, my beta bar, the adjoint of alpha bar is beta bar, which is alpha bar bar. So, you write down A alpha bar bar B. Let us do this carefully. This is equal to A beta bar B So, the adjoint of that is, so the definition of beta bar is, this is B beta A complex conjugate of that, but beta is alpha bar. So, you get B alpha bar A, and then this by definition of alpha bar is A alpha B bar bar. This is a complex number. This is the scalar product, which is a number, and the complex conjugate of the complex conjugate is the number itself. So, this is equal to A alpha B, because the complex conjugate of that is with single bar, and the complex conjugate of that of the complex conjugate will be the same number. So, therefore, alpha bar bar we have proved must be equal to alpha. So, the adjoint of the operator alpha is always is the same operator. Now, let me do little more algebra. Let us define a ket A and let alpha ket A be equal to ket P. You just have to revise this once or twice, and then you will be able to get the hang of it, and when we will work out an example, one or two examples, then things will become straightforward. So, I take A alpha bar B is equal to, from the definition of alpha bar, B alpha A with a bar, but alpha operating on A is ket P. So, this is B P complex conjugate of that. From the definition that we had introduced in the first slide, we had said that this is equal to P B. And therefore, since this holds for any ket B, so therefore, A alpha bar must be equal to bra P. Therefore, if I have ket P is equal to alpha A, then bra P is equal to A alpha bar, a relation that you must remember. We next try to find out what is the adjoint of a product of two operators. So, let me write down this alpha beta. So, therefore, we will have, let us suppose I write this as alpha beta bar. So, alpha beta bar, say bra A ket B is equal to bra B alpha beta B sorry, this should be A. Now, let me define ket P is equal to beta A. So, this is B alpha ket P. So, if I reverse this, I will get bra P alpha bar ket B, but bra P is equal to A beta bar, that is just now we have proved. So, therefore, this will be bra A beta bar alpha bar. So, we get the important result that alpha beta bar, the adjoint of the product is equal to the product of the adjoint in the reverse order. In general, alpha beta is not equal to beta alpha, they need not commute. For example, two square matrices may not commute with each other. For example, let me consider two matrices like 0 1 1 0 and another matrix, let us suppose I consider 1 0 0 1. Now, these two matrices will commute. I leave it as an exercise. However, if I consider these two matrices 1 0 and 1 0 0 minus 1. So, if this is alpha and this is beta, then you can immediately show that alpha beta is not equal to beta alpha, but alpha gamma is equal to gamma alpha. So, some operators may commute, some operators may not commute. So, a linear operator can commute with another operator, but in general they do not commute with each other. But what we have proved is that alpha beta bar is equal to beta bar alpha bar. In fact, I can do like this, that alpha beta gamma delta, if there are 4 operators, then the adjoint of that will be delta bar, gamma bar, beta bar, alpha bar. So, the adjoint of the product, is the product of the adjoints in the reverse order. The adjoint of the product is the product of the adjoint in reverse order. If alpha bar is equal to alpha, if the adjoint of the operator is equal to the operator itself, then the operator is said to be a real operator, or this is also known as a self adjoint operator, or some people call it as a Hermitian operator. So, if the adjoint is equal to the original operator, then we say that the operator is a real operator or a self adjoint operator. And what I am going to prove now, that if I write down the eigenvalue equation that of the operator alpha, then alpha a n is equal to a n a n. Let me write it down on a fresh page. The eigenvalue equation of the operator alpha is given by alpha ket a n is equal to a n ket a n, where this is a number. When I write this sign, C number means it can be a complex number, but we will show that if alpha bar is equal to alpha, then a n must be real. And how do I show this? That if this is ket p, then you will have bra p is equal to bra a n alpha bar, but alpha bar is equal to alpha, and this will be, leave some space here, a n star bra a n. We operate this on ket a n, so this becomes ket a n. We multiply on the left this equation 1 by bra a n. So, this becomes a n p will become a n, please see this, alpha a n. I am operating on the left by bra a n, by a row matrix. So, this will be a n a n a n. So, the left hand sides are equal. So, therefore, the right hand sides must be equal. That means, the right hand side, if this is equal to this, then I can write this down as a n star minus a n bra a n ket a n is equal to 0. So, there are two possibilities, either this is 0 or this is 0, but this is 0 means the trivial solution, that is, if bra A n ket A n is 0, then ket A n is a null ket, and that is the trivial solution, because alpha operating on a null ket is 0. So, it is something like this. You take any matrix 0 1 1 0, you operate this on a null ket, this will be always 0. So, null ket is always an eigenket, but that is the trivial solution. You can write down 4 here, you can write 5 here, this equation has no meaning, because the null ket is known as a trivial solution. So, therefore, this cannot be 0, because that will correspond to a trivial solution, and so therefore, A n star must be equal to A n. And therefore, we have proved a very important thing, that all eigenvalues of a real linear operator that is alpha bar is equal to alpha. This is known as the real operator or a self adjoint operator, whose adjoint is equal to the same operator, are always real. I can mention one thing, that for example, if I have a eigenvalue, if I have a matrix like this 1 0 1 0, simple matrix 0 0 0 0, and let us suppose this is boys. So, since this has diagonal terms, one of the eigenvalues is 0. So, in fact, if I operate this on 0 1 0, this is 0, it is a null ket. But please see, this is not a null operator, this is not a null vector. So, this is a valid eigenvalue equation in which 0 is the eigenvalue and the eigenfunction is 0 1 0. So, if an operator operating on any ket gives you a null ket, that does not mean that either alpha is 0 or ket p is 0. No, both can be non-zero, and this represents an eigenvalue equation, because this is as if 0 operating on ket p. But if this operator operated on a vector like this, then this is a null ket. This, even the Schrodinger equation that we had considered earlier, H psi is equal to I E psi. If I take psi as 0 everywhere, then it is 0 equal to 0. So, that is a trivial solution, that is a solution which is of no interest. So, we have proved that all eigenvalues of a real linear operator alpha bar are always real. Now, I prove one more very important theorem. So, we have proved that the eigenvalues are real. So, therefore, let me consider a real operator alpha bar is equal to alpha. Then what we have proved is, if I have an eigenvalue equation alpha a n is equal to a n ket a n, where this is now a real number. A n is a real number. Now, let me take let it have another eigenvalue A m. So, you have alpha ket A m is equal to A m ket A m, and let the eigenvalue A n and A m are not equal. So, A n is not equal to A m. I pre-multiply this by bra A n. So, I get A n alpha A m. I pre-multiply this by A n. So, I get bra A n alpha A m is equal to, let me write it down again. So, I get bra A n alpha A m is equal to A m bra A n ket A m. Let us suppose this I denote by ket p, then you know that bra p is equal to, let me put a space here, equal to A n alpha bar. If I take the adjoint of this, complex conjugate of this, A n alpha bar, but alpha bar is equal to alpha and A n is real. So, I leave a little space here, A n bra. Now, what I do is I post multiply, that is, I operate this on A m. So, I operate this on A m, I operate this on A m, and I operate this on A m. So, as you can see, this, the two left hand sides are equal. So, therefore, this must be equal to this, and therefore, A m minus A n, A n A m must be 0. So, if A m is not equal to A n, then this must be 0. That means, eigenkets belonging to different eigenvalues are necessarily orthogonal. Let me write it down. This is a very important sentence that I just now mentioned, that from this equation it follows that first of all alpha bar is equal to alpha, then alpha A n is equal to A n ket A n. So, we read this ket A n, of course, it is a non-null ket, otherwise it will be a trivial solution. Ket A n is an eigenket of the operator alpha belonging to the eigenvalue A n, of course, real eigenvalue. Similarly, ket A m is an eigenket of the operator alpha belonging to the eigenvalue A m, and if A n is not equal to A m, then we have just now proved that these two kets must necessarily be orthogonal to each other. Let me give you an example from matrix algebra. So, all of you, this is a very simple matrix 0 1 1 0, very simple matrix. and if you want to solve the eigenvalue equation, so you form the determinant minus lambda 1 1. So, lambda square is equal to 1, lambda square minus 1 is 0. So, therefore, lambda is equal to plus minus 1. So, therefore, the eigenvalues of this matrix of this operator alpha is plus 1 and minus 1. It is a Hermitian matrix, and so therefore, you will have 0 1 1 0. So, the eigenvalues eigenfunctions are 1 1, in fact, I can multiply by 1 over root 2. So, if you carry out this multiplication, I will get 1 1. So, 1 1 is an eigenket of the operator of the square matrix this belonging to the eigenvalue 1. Similarly, you can show, I am sure you have done this earlier, that 1 minus 1 will be equal to minus 1 times 1 minus 1. These are all Hermitian matrices, these square matrices are all Hermitian, and so their eigenvalues are necessarily real. So, orthonormal eigenkets of this operator will be 1 over root 2. Let us suppose I denote this by ket 1, 1 over root 2 1 1, because to normalize it I will write a root 2, and similarly the other orthonormal ket will be 1 over root 2 1 minus 1. I can also write minus 1 1, it does not matter, within a multiplicative constant, that is all right. Finally, let me give you a simple homework, that if I take the matrix 0, this is actually a Pauli matrix, some of you may be familiar, 0, this is a Hermitian matrix. So, its eigenvalues are real. And what are the eigenvalues? So, you make the determinant lambda square minus minus plus minus 1, so equal to 1. So, this implies lambda equal to plus minus 1. So, because it is a Hermitian matrix, although its elements are complex, it is a real, its eigenvalues are real, and I leave it as an exercise for you to find out the eigenfunctions of these matrices and show that the eigenfunctions are orthogonal to each other. So, therefore, these two vectors in this case, they are not only orthogonal, but they are normalized. So, we say that they form an orthonormal set, that is 1 1 is 1 is equal to, this is the normalization condition, and then 1 2 is equal to 2 1, this is equal to 0. And finally, we consider another very simple example, and that is, I take this diagonal matrix 1 0 0 minus 1. This is also a Pauli matrix. Of course, this is a Hermitian matrix, it is a self adjoint matrix. So, the eigenvalues are of course the diagonal terms, which is 1 and minus 1, and the eigenvectors are now 1 0, this will be 1 0. So, 1 is an eigenvalue. So, this ket vector 1, which is equal to 1 0, is the eigenket corresponding to the eigenvalue plus 1. Similarly, this ket 2 is equal to 1 minus 0 1 0 1 is an eigenket of the operator this belonging to the eigenvalue minus 1. Even these two sets are such that they form an orthonormal set. Ket 1 bra 1 is 1 0 1 0, this is 1 1 2 is equal to 1 0 and 0 1. So, this is 0. So, and then this is equal to 2 2, and I leave it as an exercise for you to show that this is 2 1. So, these two vectors form an orthonormal set, these two vectors also form an orthonormal set, complete set of orthonormal functions in the 2-dimensional space. It is something like this, that in a 2-dimensional space I can have this x cap and y cap as two orthonormal vectors. I could also choose this x prime cap and y cap prime cap as two orthonormal vectors, and any vector in the 2-dimensional space can be represented as a linear combination of either x cap and y cap or x prime y cap and y prime cap. So, in my next lecture we will solve the harmonic oscillator problem using the Bra and Ket algebra that we have developed.